In this module, like most of them, I've included a hands-on demo that you can download and play along with, and I encourage you to do that because you learn best when you get the hands-on learning. So for this lab, we want to decode a secret message using IDA-Py. And we're pretending that we're working with live malware, so we don't really want to execute it, although we can. It's not actually malware. You can feel free to do that. But we want to first reverse the program to figure out the key that would actually decrypt the secret message in here. We'll need to reverse that decoding algorithm. And what we want to do is write a Python script to emulate that decoding so that we can just dump the message right within IDA-Pro database without actually having to execute the program, and it'll be printed out to the message window. Now for some labs where there's a little bit more steps involved, sometimes I include something called a skeleton. So 1_skeleton.py gives you kind of a example, a place to start when you're writing the script. And then 2_Python kind of gives you a little more help, fills in a little bit more of the script, and then I have the solution as well if you need. So that when you do the lab, you can do it in stages to get the maximum learning effect without just directly looking at the solution. Okay, here we are in the lab. The executable is called scriptinglab.exe. That's what we want to first reverse engineer. And we can actually go ahead and run it. We are kind of pretending that it's malware and that we don't want to run it. But whatever, we can just run it either with a key or without a key. And we see that if we don't enter a password, it says, please enter the password. And if we do enter a password, it does some sort of decoding on some internal data and prints that out saying, here's the decrypted buffer. So the first thing we'll need to do is figure out, well, what's the password or the key to this? And then can we emulate that decryption that happens, or the decoding as it really is, and then write an IDA-Python script to do that. And you can see that I've got the IDA-Python scripts. I've got a start for it here. So if you just take a look at that, you'll see that I've kind of started to flesh in what you'll need to do as you program. So grab the executable, put it into IDA, say OK, and great. Let me just, I sometimes like to get rid of some of that so I can see the screen with more real estate. You don't have to, however you like to see the program. So here's the preamble, here's the security cookie being set up, here's a variable being set up, here's a compare to argc and jz. So what does that do and mean? So if it's 0, if there are exactly two command line arguments, the name of the program plus the password, we'll go over here. If not, we'll go over to the usage statement, and we saw that as we executed it. Here we see argv being moved into EAX. We add 4 to EAX, and what that does is basically argv is a list of string pointers, and by adding 4, we go to the next string pointer. So now we have a reference to the password, put that in ECX, push that to the stack, push a variable pointer to the stack as well, var d8, and if we click on that, we see that takes us to the stack. We can take that var 8, we can right-click it, go to array. We see that by default it thinks this array is 104 bytes. And how did it know that? It knows that. We can do that for this one as well, because it basically just looks at the stack and figures out how much space is till the next used portion on the stack, and assumes that, well, if there's nothing used in between, either there's a bunch of unused integers or whatever, or this is an array. And so sometimes what I'll do is I'll go ahead and just rename this array 104, give it a size, so that when I see it being used, I kind of have some idea what that is. And obviously we know some of what this is here. This was probably the cookie. We saw that being used above. And then the saved EBP, the return address, and the arguments pushed to the stack. So we fully understand the stack frame for main. So if we go back, we see that, in fact, yes, that was the cookie, by the way. We also see, okay, array 104, that makes more sense. We see that push. So there's 2 arguments pushed to this function, the password and an array. So what does this call do? This call basically does a stir copy. It'll take and copy the password into that array 104. So if you don't know what stir copy does, you can just Google man space stir copy, or if you have a Linux box, man means check out the manual page. And you'll see that it copies from a source to a destination. And since arguments were pushed in reverse order, we know we had password and then array, and we see that as well here. So we can go back out and just label this stir copy if we want to. And we know that this also, we could say, holds the password. We could provide more data to that so that when we see it used down here, we see this is array 108 passed into here. What does this do? We'll zoom out on this. We don't see, if we zoom in, we'll see that we don't see any calls really in this. So this is probably, we see it in a loop too. I'm guessing off the top of my head, let's just call that the decoder. And what about this? What does this function do? If we look closely at this printfs and then printfs decrypted buffer. So this is probably copying the final output into some buffer so that we can print it. So let's just call this the printer, and then you're done. Security check and you're out. So that's all this program does, is it basically copies the password into a buff, decodes, puts that into a buff, and then prints that buff out. So all we have to figure out is two things: how this decoder works and what the password is. Now if we walk through this decoder, we'll see preamble, we're setting something var 4 to 0, var 8 also, set that to 0, jump to here, move offset, what is at this location, 40B034 into ECX. If we go to that location, it's an unknown data element, and it's the stuff that's right above this here. If we can either double click it and get to this, or just scroll up. So let's just call this the encoded data, and we could call this a pointer to encoded data, whatever we want to call it. So here is the secret message. It must be this. It's in the data section, and we can see that it's not English ASCII text anyway. It's been encoded in some format. Okay. We move a pointer to that in ECX, and we add something to ECX. What is that? This is probably the index, right? If we're going to decode each byte at a time, we see that we started at 0, and we add this to ECX, and then we take a byte. This is how I knew it was going to work on it, operate on it 1 byte at a time. Byte pointer ECX, put that into EDX, and we test, and we see, is it not 0? And if it is, we'll go out. We'll be done, basically. Otherwise, we'll decode. We could call this area. So then we grab a byte again. We already have it in EDX, but it sort of grabs it again in indexes just like it did. Then it grabs something from arg0. That would be the password buffer that's been passed to this API, puts that into EDX, and grabs a byte from it. So it never indexes this, puts it into ECX, and then we XOR ECX to EDX, and then we move this arg4 into EAX and add an index to this. So this must be the final output, right? And we move that decoded byte into that buffer. So we've got our decrypted buffer basically. Then we move the index into EAX, add 1 to the EAX. That's just basically I++ or something like that. And we go back up and we do it again. So we're operating, and we're just doing a simple XOR decoding. So there's no real decryption or anything. It's just a simple XOR on a byte. So what byte would it be? How are we going to find out what the key is? Well, there's two different ways you can do it. You can either brute force it. There's only 255 choices, right? And just see which single byte outputs readable English text. Or you can use an old malware trick, and I'll show you what that is. So basically, if you XOR any key with null, you end up with that key again. So we assume that this is an English readable string, and the final byte was null in that string. And so the key must be capital A if they used a capital A to encode. So you're making some assumptions there. You're assuming it's an ASCII string and it ends with a null byte. But that's a fairly decent assumption. In fact, it's something that I've actually seen before in malware from a decade ago. Malware was very simple, And that's how they would hide the internal strings, so that as somebody found the malware and tried to reverse engineer it, you wouldn't be able to figure out what URL it was calling out to and various things like that. They decoded all their strings with a simple XOR, but they didn't realize that when they did that, the key was essentially right there in the code. So that's kind of a simple trick. So that would be the key. So now we figured out the key. We figured out how the loop works. Now all we have to do is figure out how to write our Python script so that down in the output window, which I closed already, you'll see the actual message appear. And when you have your Python ready, you go File, Script File, and then you can find the IDaPy file here. Just browse to the correct folder and run it, and that'll be how you'll run it. And again, I've given you a couple of starts as well as the solution. If you need to kind of cheat a little bit or whatever, you can start with this. We know the key was hex 41, for example, or capital A, and you can kind of begin to fill this in. We knew the address where the encoded message was. We define a decoded string, and we can add to that and finally print that out. So that's how you get started, and I leave it as an exercise for you to finish doing this lab so that you can get the experience of writing an IDaPython script yourself.